All right, so if you go to Canvas, let me show you where that thing, I mean, it's easy to find, it's right there on the top. It says review for the test, and we'll, you can open that up. We'll go over this one actually, because this is gonna be my guide for the review anyways. I'm gonna run it off of this, so I'm gonna click on that. Let's see what it says. So read the entire chapter 20. You know what? Let's make sure it is chapter 20. And it is chapter 20. All right, so you should look at everything that is in chapter 20 apparently could be on a test. Because if it says read entire chapter 20, then everything that is there could be on your test. Know how to solve all the problems assigned from the textbooks and worksheet. You will have both word problems to solve and a few conceptual questions. I actually haven't made the test yet. So I mean, you will have word problems to solve. I'm not sure if I'm going to put any conceptual questions or multiple choice questions, but that's there. Know how to draw electric field lines for various charge distributions. Oh, we got to review electric field lines. Okay. Good thing I looked at it. And then the test is not broken up into 70, 30%. You wouldn't know what that is because we've never used that anyway, so it doesn't matter. That 0.4 is irrelevant to you. Now I gave you some problems to practice with. So once I review the material, then you can look at the practice problems. They're not easy. They're at least time consuming, and then some of them are actually hard. I should go over number 7 because number 7 is not something you can solve without numerical approach. And I have a comment about it. So in case I forget, when I say I'm done and I haven't actually looked at problem 7 with you, you should just say, no, you're not done, Mr. Klappig. You still need to go over number 7 in the review. Okay, so just remember that in case I forget, because I might. So let's review whatever we need to review here. I'm going to stop this share, and then let's just go back to the screen. I'm curious actually how this recording works. Does it record the screen and therefore all of you and me kind of small so that whoever's watching it will never know what I'm actually doing? Who knows? Just in case, I'm going to make myself a little bigger. Probably should have done it last time. Oh, well. I bet you it just records the screen. So they won't really get anything out of that recording for the torque because my window is very small. It's like I have there are like 15 windows in the screen here. So, well. All right, so review of the electrostatics. Let's go ahead and start. We started with the conceptual things. So you want to go over the worksheet with the concepts that we did go over at the very beginning. So you charging by conduction, charging by induction, charging by frictional rubbing, and all of that, right? Within the atom, you have three particles. You have electrons, protons, and neutrons, and you can remove only electrons in an easy way. It would be difficult. It's not impossible to remove protons from the nucleus, but it is not something you would do in ordinary circumstances. Same thing with neutrons, but you can easily remove electrons. So you have some kind of positive charge in the middle, neutrons, this would be a nucleus, and then you have some sort of an electron cloud around this thing. It is the electrons that you can remove from the atom fairly easily. You're charging by friction. If I want to charge something by friction, I just rub the two things. They have to be dissimilar things, but I take my fingers, slide it across the board, and I've removed electrons from the board. Now I have excess electrons on my fingers. Electrons are missing over there. That's a positive charge. This is a negative charge now. It's all about the movement of electrons. You never really move protons. So at least not in electrostatics, we don't consider that. You could set up a place where you have a whole pool of protons and then you move them around, but it's, all right, we talk about the movement of electrons. So charging by friction, you take two dissimilar objects and you rub them. Bunny, balloon, recall what we did with that. This is not a balloon, but anyways, triboelectric series. There's a triboelectric series. You need to be aware of it. Don't memorize the triboelectric series, but does anybody remember what the triboelectric series does? What information it gives you?
It tells you which items are more likely to take electrons.
Yeah, and that's basically it, right? So if you get a list in a triboelectric series, you get a list of things, different substances, and then different materials. And then the higher up the material is, the more likely it is to gain the electrons as compared to the ones which are lower. Although be careful, read the description of the list because they might flip the order. And that's fine, as long as the description is present there to indicate which way the order goes, whether it goes up or down. So just remember that. So anyways, here I have a plastic, I have a bunny. When I rub the two things, the electrons will move from, well, actually, I don't know which way they'll go. I think they'll go to the plastic. I think they'll go from the bunny to the plastic, but I'd have to check that with the triboelectric series. All right, and then we also had electrons in conductors and electrons in insulators. So if you dump a bunch of electrons on a conductor, right, here's a conductor, a conducting sphere. You dump a lot of electrons right in this spot. This is a conductor. And then you have an insulator here. So this is an insulator. You dump a lot of electrons right here. Insulator, right? This could be some kind of a metal ball. This could be a balloon, for example. What will be the difference between the two? This is a conductor. This is an insulator. What's the difference? In terms of how electrons will behave. How will electrons behave in this case? How will the electrons behave in that case?
In the insulator, they can't like distribute evenly. They just kind of get stuck.
Yeah. So in a conductor, because electrons are free to move, it will not take them long to distribute themselves evenly throughout the whole thing. So you're going to get electrons all over the place here, evenly distributed on the surface, not inside of the conductor, but on the surface, right? Because they'll repel themselves, so they wouldn't be able to sit on the inside, but they'll sit on the surface. Versus in the insulator, since the charges cannot move easily, they'll just sit there. They might spread a little. But they'll just settle some more or less in that section, and they'll just stay there, right? So conductors versus insulators. In conductors, charges can flow. Insulators, they cannot flow. A good example of conductor would be any metal would be a good conductor, and because it's a good conductor because of the metallic bond that you have there. And then we had what else did we have there? Oh, why would the balloon stick to the wall? Oh, look at that, we have a balloon here. So you take a balloon, charge it with a bunny. Right? You take a balloon, charge it with a bunny, and then the balloon sticks to the wall. How come? Like the wall is neutral. We know that we started with the wall being neutral. So the wall is neutral. We charge the balloon to a negative value, some negative charge there. So the balloon is negatively charged. The wall is neutral. Why would the two stick? Yeah. Yeah, right. Yes, so you end up polarizing the atoms within a wall, right? And the reason why that happens is because electrons in the balloon will push the electrons away a little in the atoms in the wall. So if this is, actually we could just run it this way. So like here is a balloon, right? Here's the insulator, here's the wall, here are the atoms within a wall. They have positive nuclei, and then they have electrons. But these electrons, the cloud of electrons that you have around the nucleus, these electrons will be pushed a little away. So they'll tend to spend more time towards the right because of the presence of the negatively charged balloon. And as a result of that, the left-hand side of the wall is going to have more of a positive charge. So you have a plus here, and that implies minus plus will attract. So you end up polarizing these atoms here by bringing in the charged balloon. What about the water? We open up the faucet, the water flows out of the faucet. You bring in a balloon, and the water is attracted to it, right? Here's a faucet. You open up the water, you bring the balloon, and the water stream itself will sway towards the balloon. Does anybody remember why that happens? While you're thinking about it, let's see if I can replicate. Oh, wow. Actually, you can see that. I can see it on the camera. If I can see it, you should be able to see it too. I have no idea if you see it, but I can see the water moving towards the balloon. Anyways, it would be better if I didn't have this thing leaking, so I have single stream. But be it as it may. Anybody remembers why that happens?
Isn't the water molecule polarized itself? So
Yes.
The positive side is attracted to the negative balloon.
Yeah, that's right. So water molecule is permanently polar. It's just always polar because of how how hydrogen bonds to oxygen. Water molecule is polar, and for that reason, water molecule will interact with an electrostatic field produced by the balloon. Okay, so that's that. What else did we have? Charging by induction and Well, charging by conduction is almost trivial, right? Charging by conduction is just the process of dumping electrons from one place to another by basically touching the two things. So if I want to charge the sink, you can't see the sink on the camera, but it doesn't matter. Charge the balloon. If I want to charge the sink by conduction, just take the balloon and attach it to the sink. There it is. The sink is right there, just under the thing. And so the faucet rather. So electrons will be transferred from the balloon into the faucet through the process of conduction, direct contact. So frictional rubbing, conduction, and then induction. We can also charge things by induction. Does anybody remember the process of induction? How you charge things by induction? There are a couple steps involved in induction. All right, so let's run this through. I'll do it with a faucet. We'll charge the faucet by the process of induction. So I'm going to charge the balloon. Balloon is now negatively charged. I'm going to bring this negatively charged balloon to the neutral faucet. So I bring the balloon closer and closer. What happens with the electrons within a faucet? As I bring the balloon closer and closer, what happens to the electrons in a faucet?
They're polarized.
Yeah, right. So the electrons will, so the faucet will be polarized, right? And the electrons will be pushed away from this side to the other side. So you're going to end up with an excess of electrons here, lack of electrons there. So I have plus and minus. And then what I can do is I can just touch this side, and the excess electrons will flow into my hand. I've picked up excess charge, but in the meantime, I've removed electrons from this thing so that it becomes positively charged, right? So that's an example of charging by induction. You want to review these concepts before the test because it's that's part of the unit. And so I may ask you, I'm going to ask you to calculate some things, right? I'm going to give you some problems to do, but I will probably ask you some of these questions too. I haven't made a test yet, like I said, but you can expect some conceptual questions. I can't remember of anything else there in the concepts, but from that worksheet that we did. So I'm going to move on to other things. All right, the charge of an electron, the charge of a proton. We already went over that in this session, but you had E is 1.6 times 10 to the minus 19th coulombs, right? That showed up in some of the problems I gave you there before. This is the charge of a proton and the charge of an electron. The difference is that one is plus, one is minus. You may need the mass of an electron, you may need the mass of a proton for the test. But like I said, if you do, I'll give you that. You can memorize it if you want to. You can add it to your equation sheet, but I would just give you that, I think. Suppose that, I don't know, let's leave that. Okay, fine. Force, I think that's it. So then the force, electrostatic force. Okay, positive charge, there's a force, repulsive force between them, right? So the force points this way and this way. Positive charge and negative charge, there's an attractive force between them, so this goes like that. Negative charge and negative charge, there's a repulsive force between them, this goes like this. Positive and neutral will give you an attraction because the neutral object will be polarized. What I'm talking about here is the balloon in a wall, right? Negative and neutral will also be attracted if the neutral object can be polarized. So again, I'm speaking about a balloon in a wall, essentially, right? Although if you have a neutron here and an electron, the two will not electrostatically attract. If you have a neutron and a proton, the two will not electrostatically attract. Anyways, there's a force between these, and the force that you calculate between these depends on the distance d. We used the r, didn't we? I think we used the r. Sometimes I use D, sometimes I use R. So I don't know what we had here, but the force is going to be K, Q1, Q2 over R squared. You have seen this before, so this is not a surprise. Q1 and Q2. All right, now if you're in 2D, so let's say you have a charge here and you have another charge here, and you have another charge here and you want to figure out the force on that one. Then what you would end up with is F1. You would end up with F2. And then you have to write out F1 in a vector form, you have to write out F2 in a vector form, and then you add them up to get Fnet. All right, to find Fnet, you would have to do F1, F2, add them up to get Fnet, right? All right, so remember that, pay attention to the signs. For example, in this case, X would be negative, Y would be positive. Here, X would be positive, Y would be positive. If the charges differ, so for example, if you have a picture that looks like this, minus, and here's a plus, right? If this is what you have instead, then you pay attention to the signs. So what you would have is force of attraction here. You would have force of attraction here, but you would still have the same process, F1 and F2. And then you would find an expression for F1 you'd find an expression for F2, and then you would find F net. Right now, but in this case, F1 would have negative for X, negative for Y. F2 would be positive for one, but negative for the other. So pay attention to the signs. Depending on what type of charges you have, you will end up with positive or negative components of the force. All right, so that's that. Now, the other thing to contrast here is the electric field. So let's move the camera. You have similar problems in electric field to the electrostatic force, electric field in 2D, but don't conflate the two. Well, in the first place, suppose you have a charge and this charge sets up an electric field. So you have an electric field, points like this. If you want to calculate electric field at some point, maybe you want to calculate it at this point, right? You want to figure out what is the strength of this electric field here, some distance r away from the charge. Well, that would be K Q over R squared, right? And electric field by convention always points away from the positive and always points towards the negative. So if you have a negative charge, electric field points towards it. This is by convention. They have to be, they cannot be the same for positive and negative. So if one points away from the positive, points towards the negative. The equation is the same, KQ over R squared. So if I have some Q here, that should be Q. If I have some Q here, and I want to figure out what is the electric field at this point, it will point towards the charge, but it's going to be KQ over R squared. All right. Now, if you're in 2D and you have to calculate the electric field, so for example, here's a plus. Why don't I do it like this? Yeah, plus and a plus, right? And this is entirely separate from that, so don't confuse these pictures here. I'm gonna erase some of it. So this here, these two charges are entirely separate from that, has nothing to do with this here. So you have these two charges in space, and the question is, what is the electric field at this point? Actually, let me make 1 plus, 1 minus. 1 plus, 1 minus. So what is the electric field at that point? Well, it would be electric field from this charge, so maybe call this E1. Note that I drew it pointing away because it is away from the positive. But here, electric field due to this charge would be pointing towards it. E2. Why is it that it's pointing towards it? Because electric field of a negative charge points towards the negative, right? See there? And then see here. So away from the positive towards the negative. And then you would have plus, plus for the components, and then you would have plus, minus for the components, right? E1 has two positive components, E2 has positive, negative component. You add these up to get E net. So E net would just be the sum of these here. Let me do one more. So let's say you have like a, let's say you have a positive, negative, and a positive, like this. Right, so plus, can you guys see this well enough, or is this too small? Maybe it's good. So plus, minus, plus, and the question is, what is the electric field at this point? Note that there's no charge here. When I'm asking for the electric field at some location, I'm asking for electric field at a location. But there's no talk about charge at this point here, right? So due to that, electric field would point away. So this would be maybe E1, if I label that as charge 1. Due to this, electric field should point in this direction. This would be E2, if I label this as Q2. And due to that, electric field would point like that, and maybe I would label this E3 if it's due to Q3. So electric field always points away from the positive, always points towards the negative. And then I have to find the XY components of this, XY components of this, XY components of this, add it all up, get F net. Not F net, but E net. All right. Finally, to combine the electrostatic field with the electrostatic force, what we could do is we could clean this up. And let's say you have an electric field that points like this. All right, so here's the electric field E. And in that electric field, you place the charge Q, maybe a positive charge Q. It's going to feel a force, right? There's going to be a force on it. And then that force, F, is Q times E. And you've seen it multiple times. So there's that. If it's a negative charge, so maybe you place a negative charge here, that negative charge, due to the field, is going to feel a force in opposite direction. Right, but it's still going to be same expression. Of course, there's a force of attraction between these two, but that's a different story, right? We're just looking at the force generated on the charge by the field itself. And then the last thing is the electrostatic torque. All right, the torque on a dipole. So you place a dipole in the electric field, and there's going to be a torque. But this is what we just did, 20 minutes ago. So I don't think I have to review that. Okay, so there's the review of all of the concepts, and then I can't think of anything else. I think what we'll do. There's a question, yeah.
Number 7.
Yes, that's right. Good. It's a good thing somebody's paying attention. So let's go look at number 7. And number 7 is hard. Let's do that one, right? And then I'll give you some time to work with the other problems, and then if you have questions on them, you can ask them. But let's go look at number 7 off of your review sheet. All right, let me pull this up so that I can actually see it. The last problem on your review sheet. So figure shows 2 5-gram spheres suspended from 1 meter long threads. I'm just gonna copy the picture. What am I looking for? What is the angle? And I have the charges, okay. All right, so here's the picture that we have for number 7. Off of your review. Charge, they're both positive, so plus, another charge, plus. I have 1 meter, angle theta is indicated above, okay. So they want us to use this as theta. Of course, this is also theta. So you have theta here, theta there. I have the mass of each. So this is 5 grams, and this is 5 grams as well. And then I have the 2 Qs, right? There's a Q here, and then there's a Q there. So I'm just gonna label this as Q and Q, but the charge is 91 nanocoulombs. Wait, minus? Spheres repel each other after being charged too. Oh, okay, so the text talks about negative, but the picture gives us positive. Oh, well, we'll just make this thing positive. So we have 91 nanocoulombs for each one. What am I looking for if I have everything? Oh, probably the angle, right? Yeah, what is the angle? Okay, so Q is 91 nanocoulombs. The text should say plus 91, because the picture shows the plus, and then, anyways. All right. So this is an equilibrium. Nothing is moving anywhere. It just sits here. So F net is going to be 0. Right? All of the forces acting on this charge have to add up to 0. All of the forces acting on this charge have to add up to 0 because the charge is not moving. Now that means that I have to determine all the forces acting on these things. So what 3 forces do I have? How much time do I have? All right. Yeah, I mean we're supposed to have the wellness check. So we will probably. All right. So hopefully it's clear enough that I have 3 forces acting here. One is the weight. Right, so I have the weight, which is mg, and I have the mass, so I can calculate this. I can find the numerical value of this fairly easily. I have the tension, so here's tension. Now this tension is going to have x and y components, right? It's going to have the x component, it's going to have the y component. So maybe let's indicate that. Well, actually not yet. The third force acting on this charge is the electrostatic force of repulsion between these two, right? They repel themselves. So there's going to be an electrostatic force F. I'm just going to call it F that points this way. Now the distance here between these, oh, I can figure that out. Right? I can figure out the distance. Here's how I can do it. I'm going to need that distance. So let's do some geometry on this triangle first. This is 1 meter, and then this is 1 meter. I have 90 degrees here. So if I have 1 meter, I can't. Never mind, because I'm looking for the angle. So I'll have to play around with this. But anyways. The equation that I would want to use for that force is going to be, you have 2 options. It's either going to be Q times Z or KQQ over R squared. Now, given that you have these 2 charges here, you would want to go with this one. KQ times Q over R squared, where r is this whole distance here. All right, so I can find an expression for this. Here's my expression for f, then there's tx, so I have tx here. Tx is equal to that f. I'm gonna put this on the top. Tx is equal to f. And then ty, which sits here, ty is equal to mg. So I'm gonna put here ty is equal to mg. All right, well, I can calculate mg pretty easily because I have the mass. So mg and ty is known to me. If I have ty, I may be able to do something. Well, here's the angle, theta. So what I could do is I could write tangent, let me add another equation to this. Tangent of theta would be tx over ty. And so going off of this equation, I can then write tangent of theta equals, for tx, I'm gonna put that expression f, which maybe I should take another step here. So tx is k q squared over r squared. R is the distance between these two. So for tx, I'm gonna have k q squared over r squared over ty. Now ty is just mg. All right, so I still have to find an expression. I have two unknowns at this point. I know q, I know m, but I have two unknowns. I have r and I have the theta. Now theta is what I'm after. So that's good. I want to have theta as my unknown, but I don't want to have r in here as an unknown. Now r for this specific problem is the distance between the two charges, right? This is r. So what I could do is why don't I call this x and I call this x as well? X is the distance to the middle here. Right, and I can find an expression for x. X is just going to be sine theta. But let me do it so sine of theta, if I look at the sine of that angle theta is going to be x over 1, right?
Mr. Clapic,
Yes.
could you explain why tx over ty equals the tangent of theta?
Oh, sure. So see this little triangle here, the blue one?
Yes.
So this blue triangle is similar to that purple triangle, right?
Yep.
Okay, so that angle theta here is the same as this angle here, because this little triangle is similar to the big triangle. So I'm looking at the blue triangle when I do the tangent, and I have 90 degrees right here. Now tangent is, what was it, opposite over adjacent, right? Tangent is opposite over adjacent, so tangent of this theta is equal to tx over ty.
Okay, that makes sense. Thank you.
Okay. Yeah. Right, and so I had that, and then I ended up here. Okay, now what I want to do is I want to find an expression for r. R is equal to 2 times x. Right, r is 2x because I labeled this as x and I labeled this as x. But look at this triangle here. Sine of that is going to be x over 1, right? Sine of theta is x over 1. In other words, I have my expression for x. X is just sine. So I'm going to put here sine theta is x. And that gives me an expression for r. So r is 2 times the sine of theta. Let me give you a minute to look at this, make sure you understand that. Right, sine of theta, sine of that angle is x over 1. And that's just sine of theta is x. But I want an expression for r, and r is 2x, so r becomes 2 sine theta. So here's what I have. An equation that does the trick, but it is an ugly equation, right? What I have here is tangent theta equals k q squared over r squared, but instead of r, I'm going to put 2 times sine of theta squared over mg. Now in this equation, I only have one unknown, which is theta, so that's good. But there's no way for you to rearrange it in such a way that you have theta equals. You will always have theta on one side and then theta on the other side. So there's no way of solving this equation other than numerically or graphically. Let me simplify this a little though. So if I have that, then this becomes tangent theta times the sine squared theta equals, I have K Q squared over top, and then I have 4 times mg. All right, so this may be a little easier to see, to notice why this equation is difficult. It's impossible to separate theta out by itself. You can't rearrange this equation such you have theta equals and then some expression where you can plug in the numbers. So in that case, you would have to solve it numerically or graphically. Now, on the test, I wouldn't give you a problem like this. But what I expect you to be able to do is to set up this equation, this equation, this equation, and get to here. And you should be able to do that much. And then, you know, numerical solution, who cares about it? We can, that's whatever. It's not, I mean, you should know how to do it, but I'm not going to test you on how well you can handle numerical solutions. Or graphic, can you solve this graphically? Sure, you should be able to do it, but that's not going to be, I'm not going to give you that on the test. Anyways, here's problem 7. Other than how you proceed from this point on, does that make sense? Okay. Now, there's a trick. Actually, you don't need it for the test. I was going to say there's a trick for small angles. You can approximate this to be a sine of theta is basically the same thing as tangent of theta, but no, you don't need that. It's more information that you don't need for the test. So my guess is that your best use of time would be to look at the other problems on review sheet and see how you do with those. All right, I'm gonna stop recording now and see if this thing will actually save the file for me. I have a feeling that the first thing we recorded for the torque, it's not going to work for those who weren't here. But maybe the second one will work. So maybe use the next couple minutes here to look at the review, the other problems in the review. If you are not staying for the lab, then you are free to go. Test is on. Oh, actually, you know what? Let me think about it. Because that part of that lab would be helpful maybe for the test. Yeah. And let's just use this wellness check to make sure that everybody gets an equal chance at this test. All right, let me give everybody an introduction to the lab. So don't go yet. This should take about 5 minutes. I don't think it will take more, but you should see the problem. We've done something like this actually, I think, in a class. Although sometimes I confuse you guys with 1402. I'm not really sure who did what. So what you will do is you're going to deal with a problem like this in the lab, where you set up a charge. It's going to be a balloon, and the balloon is going to have some charge here. We're going to label this as Q. And then you're going to have a bunny. You're going to charge up the balloon and a bunny. Balloon's going to hang here, and the bunny's going to hang here, right? And I'm going to draw a bunny here. Am I going to draw a bunny? How am I going to draw a bunny? I'm not going to draw a bunny. Well, look at that. Now, if you rub bunny with the balloon and the balloon gets a negative charge, then the bunny gets a positive charge, right? So we're going to put a big plus here for this guy. And if you transfer some charge over there, and then that is the charge you lost. So Q and Q, the two Q's must be the same. And if you rub bunny with a balloon, whatever you lose is what's transferred to the other thing. So you have two Q's which are the same. Now, in the lab, you will measure the distance between the two. You're going to measure this distance here. Call this R. You will also measure the angle. Call this angle theta. You will know the mass of the balloon, whatever the mass is. And then you will be able, your goal is to figure out how many electrons you have here. How many electrons you have actually placed there. In other words, you're looking for Q. And for those of you who are staying for the lab, there's a little more that I have to add to it, but that's fine. For those of you who will be leaving, this is basically all that you need. So can you calculate Q given the setup here? Now there are 3 forces acting on this. So let's maybe draw the forces. We have the force of electrostatic attraction. So you have F, you have the weight, here's mg, and then you have the tension, here's T, and of course you have Tx and you have Ty. On the side, I'm gonna write out how these forces work out. So you know that Tx is going to be equal to F. So Tx is equal to F. You know that Ty is going to be equal to mg. Ty is going to be equal to mg. And then that angle theta is the same as this angle theta. So you end up with, can you still see it out here? I think you can. Let me know if you can't because of the glare. Tangent theta is Tx over Ty. All right, so between these three, you should be able to figure out Q. And this problem is a lot easier than number 7. All right, so now everybody has seen that as well. So you're all equally prepared for the test, I suppose. Those of you who will be doing the lab on Friday, you'll actually take the bunny and you'll wrap the bunny with the balloon, or at least those of you who are here and the rest will watch. And then you'll have to submit some stuff. But questions on the test before I let you go? Questions about the test? Yeah, the test is Friday, yeah. I did not make it yet, but I'll probably make it tomorrow, maybe today. Maybe I'll make it today.
Is there going to be equilibrium on it?
Are there going to be problems in equilibrium? Yes, in a sense that you can expect something similar to this, for example. I'm not saying you're going to get this problem, but you can expect something similar to this, right? This is an equilibrium problem. Other questions on the test? If you want to get some extra help tomorrow, you can. I'm going to get vaccinated apparently at 1. So I can't do anything for you at 1, but prior to 1, maybe between like 8 and 12, if you want to see me, you can. And let those who couldn't be in class here today, you can let them know that if they want to see me, they can see me between 8 and 12, and I would probably give them priority. You can also try to reach me probably after 2. You can, yeah. It's just me coming out here, getting the shot, going back home. So you can try to reach me at 2 as well. And then of course Thursday after school should also work. Yeah. Yes, you can. Any other questions from you guys on Zoom? Because you're staying anyways.
Mr. Klapik, I have a question.
Yeah. Yep.
Should I tell Thomas that you're gonna like post the recording on Canvas or something?
Yeah, let them know because it was. Did Brenna come back? Did Brenna show up? Or?
I don't know.
Brenna didn't. Okay, so yeah, and you let Brenna and Tom know that I'm gonna post these recordings on Zoom, not Zoom, on Canvas. I don't know how well the first one worked out because I don't know.
Okay, yeah.
Yeah, but the second one, I think the review worked out okay. Speaking of which, I should probably stop this. Did I stop it? I think I did. All right, any other questions? All right, so in that case, those of you who are not staying for the lab, you are free to go, and I'll see you on Friday. Remember, Friday is a test, okay? So see you. And those of you who are staying for the lab, let's take a break. Let's say, why don't you guys come back at like 9, 10? All right. And in fact, what I'm going to do is I'm going to end this session so I can see if the recordings have been recorded. So I'm going to end this section, but then come back at 9, 10. All right. So see you guys.